Hello everyone, welcome to part 4 of this breakdown of Project X. Well, I think the cat's going to be out the bag in this one, so I'm going to put a link to Richard's channel in the comments because it's to do with a soldering station. In this part I want to talk about thermocouples. I did a little bit about thermocouples when I did my hot plate. I'll just bring that up. Here we are. So in my instructable for my hot plate, I talked about thermocouples here. And if we look at this diagram here at the bottom, we can see we have two wires that are welded together in a blob. I can show you a close-up, I think, if I get the right one. There, that picture. So they're actually welded together here. Basically, these are two different types of metal, and where they join together creates a thermocouple like this. And if you heat this thermocouple up, it will create a voltage where the two different metals join each other, and then this voltage obviously goes down the two wires. Ones are called typically in a K-type thermocouple we have a wire made of chromel and we have a wire made of alumel. It's an amalgamation of aluminium and something else, and this is an amalgamation of chrome and something else. And then these wires don't have to be that long, because all the actual working of it is done where the two actual metals join each other. But when you buy them, it's cheaper for them to just give you a full length of wire, and then you join it to a screw terminal, and then from there you just use copper wire going to a voltmeter. But the actual voltage, the potential difference, is very low. We're talking about millivolts. So if you actually, it's best just to wiki it actually. So if you just wiki K-type thermocouples, it'll give you a bit more information. I just bought one of them, stripped it down, and I just used the bit with the blow on the end. If you get one of these, hang on, let's just go to my picture. Let's just reduce that. I've got one here. Here we go. I bought a couple. Basically, that's what I bought. I bought one of them. It has the thermocouple inside this sensor part, and the actual wire, the whole wire, is actually the two different types of element. And when I did my hot plate, I actually had a bit of the cable left over. So this was off-cut from the previous cable, but because we just need a joint of the two dissimilar metals, let me just see if I can get that in focus. There. I don't know if it's going to focus on that. Let's just try and hold that and click on it. So the black one is made of one type of metal, and the one in the other one is made of the other metal. And I just got it red hot and twisted the two metals up together in a spiral, and this will do up to certain temperatures. But if you go into really high temperatures, you need them actually welding together. And I was thinking, actually, what you could do is, you know, the spot welders for welding battery tabs on the rechargeable batteries. If you got one of those battery welders, spot welders, you could actually spot weld the two wires together, and that will make you a new one, and you can use your offcuts of wire. So let me look at my picture again, see what we've did. Yes, so like I say, the voltage from these two wires is in millivolts, and so we need to amplify them and to read the voltage for a microcontroller to read. Well, the normal way to do this is to use a dedicated device, which is one of these. We could use a Max 6675. The two wires come in here. They are polarized, so there is a positive and a negative. But basically, what this is a amplifier, and that amplifies the voltage to a voltage that we can actually read, and then we can read it with the microcontroller. So, why am I talking about thermocouples? Well, today's modern soldering irons use these type of tips. They come in different sources and what have you, and they plug into, you know, I have this TS101 and I think it's brilliant, but there is actually a thermocouple in there, so let's have a look inside of one of these. Well, I'm not going to cut one of these on, they're not cheap, but I've drawn one, so just give me a minute and I will bring up my drawing. Let me just find out what I've done with this as well. Right, I'm just going to pause and set things up. Right, okay, so this is my TS101, and I've actually drawn it. This looks pretty much like what? Oh, wrong button. Yeah, that's more like it. Right, yeah. There we go. So that looks like my my little TS101, and what we're interested in is the actual tip. So what I can do, if I turn off the handle and turn off the anti-slip, there we have our actual tip, and that plugs in and it connects via this ring and this ring. This is actually earth, not ground, so this is so you know, if you do it, you know, the whole thing here, you know, yeah, the whole thing, the whole metal part of it connects to a little, hang about, let me just bring that up. Yeah, can you see that little screw on the end there, at the end? This one. You can put an earth lead, so you can earth out your soldering iron, and you don't. So that's what this metal bit will actually connect to. So let's bring that back. Yes, and so we only have two connections, and what we have in here is a heater element, and we also need to know what the temperature is. So what I've done is I've actually done a cut through drawing. So here's our cut through. Oh, actually I've turned it around, so that's what it looks like, and I've actually cut it open and drawn what's inside. So yeah, we can see that. So what we have at the bottom here, this yellow bit is our plastic insulated bit, you know, this piece. Then we've got our two metal rings. One ring connects to this wire. This will all be insulated inside here as well, so, but I haven't drawn the insulation. And this ring connects to this wire, and it goes up in the centre, which will be insulated as well. And so we go up the centre of the shaft, and we come to the heater element and the tip. So This tip will probably be sort of like chrome plated copper or some good conducting metal here, and this is our coil inside. The coil itself will be potted in a clay of some sort, stop any shorting, so it'll be setting like a clay or a hot, something that'll take hot temperatures. And so we've got one wire coming up to one end of the coil and the other wire coming up through the coil, and it comes to a welded junction here. And you can see that I've created two different coloured wires here. One's a red one and one's a blue one, and they're welded into a thing. And one is connected to the other end of the coil. So basically this is our thermocouple. Our thermocouple junction, just like the little blob on end of your little test, your temperature sensor leads that you use when you're plugging a thermocouple into your meter. In fact, actually, yeah, right, I just thought of something, guys. I'll come to it and I'll set it up later on, actually. There's another trick we can do to test this as well. So, I just hope that you can understand what's inside your soldering iron. So basically you've got a heater element that's potted in like a clay or some fire cement or something, to hold it and stop it touching anything and keep it insulated. And then we have a thermocouple at the end, like I've showed you in the instructable. So what I'll do is I'll just pause it again and I'll just draw this circuit so that we can make it perfectly clear. Okay guys, I've drawn a circuit of what we've actually got, and this is actually our tip. Actually what I'll do is I'll actually just draw a board around that. And I'll just put some text. There we go. There. I just wanted to draw it so we can actually see that the two pins, the two connections at the end of the soldering tip, there's just two, and obviously there's an earth that goes around the whole thing. And this is how we draw a heater. This is a circuit symbol for a heater, but what I want you to do is actually draw it like a coil, so you can see that we're actually using a coil of wire as a heater, and not a PTC. PTC. God, I get those letters the wrong way around. Anyway, not one of those other types of elements. It's actually a coil of wire, and they all connect in series with the thermocouple. So what happens is, when we apply current to these two terminals, we actually heat up this element. This thermocouple is just acting as a joint in the wire. The current comes in, goes through the coil, heats up, and the current returns to ground. So that's what happens. That's what we do when we heat up the coil. Now the thermocouple is not doing anything at this point. It's just actually acting as a joint in the wire. But the soldering station will actually send in a pulse width modulation into the tip to apply a voltage, to alter the current that the element is getting heated up with. But as the microcontroller turns on like a MOSFET to turn the current on with pulse width modulation, we have an on state and we have an off state. and once it warms up there's going to be quite a big off state than there is on state, and while it's in the off state the microcontroller will take a reading from the thermocouple. So when it's in the off state and there's no current being applied to these two terminals, we can actually apply a meter to these two terminals and measure the thermocouple, what the thermocouple is outputting, and we can read that voltage and determine how hot this element has got. And then obviously the microcontroller will then adjust the current being applied through pulse width modulation to either warm up this coil hotter or sort of just keep it mildly warm-ish, if you know what I mean. So yeah, I am going to pause it there for a moment. Okay, so as Richard has already shown on his channel, I'll put a link in the description. He's shown that we have a thermocouple inside our soldering tip, and so what I've got, my multimeter has Bluetooth, so I have written this program so that we can see on the screen my the reading of the digital multimeter. It works off taking readings and then converts the readings into a visual display similar to what my multimeter looks like. I've also got a plot. We can actually plot the voltage or the output, and we can control it here. The only thing I can't do with my application is turn the knob on the multimeter. That's a physical thing. Until they bring a multimeter out that's totally digital, totally remote controlled. So anyways, what I've done is I've attached two wires, as you can see, to the two terminals of the thing, and what I'm going to do is attach my multimeter. I've already determined the yellow one's the red one. So this is what Richard showed you. Let's have a look. I put my meter onto this end here, and what I am going to do is I'm going to bring in my little handy thing, because what I am going to do is warm it up. There we go. So that's in my little holder, my grips, and so we've got this wired up to my meter, and at the moment it's showing 0.05 volts, millivolts shall I say, 0.0 millivolts. So you can see that the voltage is very low, and the sun's come out, and I've got my little torch, so let's just warm the end up. And we can see it right. Oh, I was watching the screen. Hang on, let's get this sun out of the way a bit. There we go. So there we go. So we're up to about 2 millivolts. Let me just warm it up until the solder's sort of soft, and you can see that we're going up to. So we're only up to like 4 millivolts. So like I said, it shows that the voltage is very low. So we need to amplify that. I'll just turn this off before I set fire to place. No. So close it more. Yeah. Get rid of the sun. Go on. No, shut it on. There we go. Right, I've got rid of the sun. Yeah, my wife's just closed the curtains for me. Sorry about that. Right. What was that? Yes, it's a lot better anyways. Right, yes. So we're talking millivolts, and what I said, we normally use one of these here, and I've got one of these wired up to my Arduino. So let's wire one of these up. Tell you what, I'll just pause it and wire that up. Right, okay. Ignore my meter for the moment. It's not connected to anything. What I've done is we've connected the leads from the soldering tip, and I try not to touch it again. I burnt myself. Right, so and what I've done is I've attached this. What's it called again? Yeah, it's called a Max 6675. Right, so and obviously we have. Let's see that you can see that it's polarized. We need to put the positive to the positive and the negative to negative. Because basically what this is, the thermocouple is actually doing is acting like a heat battery. The more heat, the more the battery gives out. That's the simplest explanation I can give you. And it goes through this little chip, and this little chip talks to my little Arduino. So I've got an Arduino in the corner here. Where are we? Down in the corner here. You don't really need to see that. It's got some code on. But I've also got attached my little OLED display, and you can see at the moment there, if I get it in the right thing, you can see there thermocouple is reading 70 degrees at the moment. Let's see if I can hold it in that position, because it looks alright. Oh, hang on. No, that didn't work. Yeah, how's that? That don't look oh. Yeah. Hang on, let's try a lump of lead. No, that's too heavy. Or is it? No, let's put the lump of lead behind it. There we go. How's that? There we go. Right. So you can see my temperature. Can we focus any better? There. I really mess things up, don't I? Right, okay, so anyway, you can see that it's reading 58 now, and it's slowly dropping. So what this is doing is this is reading the millivolts, the very tiny little millivolts from the thermocouple. It's amplifying them, and then it's converting it to a value that my microcontroller, my Arduino Nano, understands, and then my Arduino Nano is outputting a signal to the OLED display that actually displays a value. So yeah, that's good. Right, yeah, so just to check, what I will do is get my torch again. Right, so get my torch on my soldering tip, and we'll warm it really up till the solder melts, sort of thing. And you can see a temperature in degrees C, so you can see that as it heats up, I'll just get it a bit closer. There we go, really close now, isn't it? So we're heating that up and we're getting a good value. And we can see the range is in what we want, sort of like 200 to 400, don't we? So we can see that we're within that range, and it works. Okay, so end of that experiment. What I'm going to do is I'm just going to pause again. I want that to cool down, because last time I tried to do it too quickly and I burnt myself. Okay, well the next step is let's have a look at the datasheet of the Max 6675 and see what it's actually doing. You can get a lot of information. Sometimes you just need to know what values it is, but in this case, because it's for Project X, I want to see actually how it works. So let's have a just scroll down through the database. Oh, well, you can see there that we've got the thermocouple there, and when it goes in, we stick a nice little decoupling capacitor across there to keep a nice steady voltage, and then it goes through these three cables. This is a cable select. If you've only got this one chip, then you can just simply set that. I think it's low for active there. You got the little dash on over the top, and then we've got the clock and the data here, which talks to the microcontroller and tells it what temperature this is here. So we want to know how it actually works. So let's just scroll and see if we've got internals. That's the data clock coming out. That tells you how the data is sent. This is I2C, I squared C, which, well, I just say I2C. It's easier for me to actually say. But this is, so you have a clock signal. Oh, well, obviously you have a cable select which goes down to ground. Then you have your clock which pulses at a certain rate, and then each tick time it pulses, there will be a signal. There'll be a high and low for the data. So there it tells you what these are, and from this data we can actually write some code to translate it. But we're not going to do this because we're not going to use one of these. We just want to see how it works, because the Project X actually uses an amplifier. Here we go. So here's a block diagram of what's inside. So you can see that we've got our two terminals at this left hand side. We've got the T minus and the T plus. It's got some switches so you can do magic and turn things off and on. Actually, I'm just wondering if this S1, it could, I don't know. Actually, no, sorry, I digress. Yes, so you can see that we've got a standard operational amplifier. Hang on, I've just learned how to use these tools. Here we go. So this bit of the circuit, down to there, down to there, and up to there. Well, actually, I don't think it's this. I think it goes in there like that. There we go. I don't know how to erase that bit. So there's our feedback resistor, and here's our voltage reference. Yes, this is another subject for another. Well, it could be in this video. And, I also want to just bring your attention to this called junction diode. This is an important thing. Obviously, Richard, I think, went over how operational amplifiers work. It's not my field, but I just know the basics. You just have a feedback where you can set the gain, and then you have a reference voltage, which this one compares that voltage, and it outputs the voltage compared to these two values. So if you've got like half a millivolt coming in here and you've got a gain of 100, it will come out at 500 millivolts here, sort of thing, and so on, basically. So yeah, and that just goes through another. I think this is just a. It just smooths things out a bit. I think it's same in, same out, but it sort of gets rid of all the interference. And then we've got our clock, our serial out, and our cable select. So this is the important bit. This bit here. Let's just get rid of that. Yeah. So this is the important bit. This is what we need to make up, basically. We need to make an operational amplifier so we can actually amplify the voltage coming in from this T plus and bring it out to a voltage that our microcontroller that can use. Now, so we're not actually using this bit because we're actually connecting our microcontroller here, and we're going to have our microcontroller do everything on the PCB. That's what the PC does. And of course, I will bring up what the cold junction is. I need another picture for that. One moment. Right, yes. What I was saying about the cold junction. Let's call this end here, where the actual two wires meet, call it the hot junction. And what we can do is call this end here of the two wires, where the two copper leads join, the cold junction. So where we're actually connecting to the two wires, it's slightly different with the soldering iron, but in the case of my hang on, let's have a look, see if I did a circuit diagram. Yeah, here we go. So in the case of my heated hot plate, you can see that we have it connected to the actual thing here, and then goes to the PC, to the microcontroller, and so we actually have a cold junction. But our tip is going to be all around this little area here. There is a cold junction still, but you won't think it to be a cold junction because it's in the tip, but it's the other end of the wires basically. So if we look at this, it's the other end of these two wires here. And these other two end of the other two wires also give a value, and we've got to compensate for this value when we're doing the calculations for the value at this end here. It's like a add it to or subtract it from type of thing here to get the correct actual voltage. You know, we have a voltage on this end here when it's cold, and we have a voltage here when it's hot, and so we take one from the other. I think that's what it is anyway. It's how I sort of view it. Yeah, so I'll just pause it to the next step. Alright, so now the cat's out of the bag, and we can see that we're working on this, our project, well, towards our project X, which eventually will be our own soldering station. It'll either be this one with our software on, or if I can get this one working, it will get this one working. But if not, we're going to make our own based on this very similar situation. And you can see that I've actually broken this circuit diagram into areas, parts. We've got the VC, this blue area, this is the VCC, which is our 5 volts in. We've got this red area here, which is our soldering iron power coming in. All this is all being described by Richard. This comes in, it comes through a MOSFET, and it adds power to the soldering iron. I'll go into the pulse width modulation side of things in the code for the ATmega. I think I may have to do this as a separate thing, so just the code actually for the ATmega, there's an Arduino way of doing it, and then there's the ATmega way of doing it. The ATmega way of doing things is more complex. Arduino way of doing things, we can just use somebody's library. It's all done for you basically. And we just use a library, and we tell it what we want to come out. So that'll come later. And then you can see what we're working on now, which is our thermocouple, which is the two wires that come up to the op amp. You can see that this area is very similar to what happens inside the Max 6675 here. So we've got an op amp, and that's what our op amp is there. We could have used this one here to, like this one here, just to do a bit more filtering, but we're just using the one. It's been made as cheap as possible, I think, this. Yes, so we get a voltage out, and then we actually come and we read this voltage. So I will just make one of these for now. Just give me a minute. Oh yeah, and sorry, I've already done this user interface. So I've done the encoder bit. Well, I did the 7-segment display first. Showed you that working, and then I did the encoder bit. So we now know how to alter these numbers with this encoder, and we also know how to alter these numbers with the microcontroller. And so our next step, like I say, is this purple area where we're actually getting the value from the op amp, and once we get that value from the op amp into the microcontroller, we'll get the microcontroller to display on the 7-segment display. Right, I'll just get that set up. Okay, you can see I've got my meter on the output of the op amp here, and I've got and the ground, and I've got my wires from the soldering tip. One goes to ground and one goes to the input of the op amp, or one side of the input, the non-inverting side. And there's our little chip, our little op amp on our breadboard, and some resistors and the variable pot. What I've done is I've used the same circuit as we have for the soldering station. So let's just have a look at that and recap. One moment. Okay, there's a recap of the circuit for the soldering station. We can see that we've got the well, Rich has been through this, and we've got the two. Basically, we've got the negative and the positive side coming up. So we've got our positive and negative going in, some resistors, depending on the tip plugged in, depends on what the resistance is. Obviously there's an R2 with an asterisk here, so there must have been some notes somewhere which I haven't got a clue where they are. Anyways, so while we're on this PD3, I think this is a reference for this A. I think what this does, I think that one that goes to A is just so you can stick a meter on and check that the reference voltage is doing what it's supposed to be doing on PD3. That's all that is. Anyways, so we're looking at this. So what I've done is I've just made this same circuit. I haven't used any capacitors at the moment, so you've got to bear in mind, because I haven't got any capacitors on there to smooth things out. I'm just too lazy. I'm on a breadboard, and quite frankly, the breadboard is going to do a load of shit anyway. So here's our circuit. So if I move across, I've just done the same circuit here. This is what's on my breadboard at the moment. We've got the feedback circuit, which has got one to stop you going too low, and then we've got the one that you can increase the gain with. So so basically, if you wind this down to 0, we're still going to get 150k. But then if you wind this all the way up, you're going to get another 100k on top of that, and it'll take you to 250k. That's on your feedback there. We've got, I think this is just a current limiter to the input on the microcontroller, just in case any spikes happen to get past this over voltage protection. Basically what we've got here is we've got a 24k. This takes the load um, uh, you've got two diodes here. Basically, diodes don't start conducting until you've passed their forward voltage. You've got, the 0.6 volts. You've got to get it higher than 0.6 to actually get past the diode. And then what happens is, if you get past that voltage, so we have the first diode, we have our thermocouple, which is inside the soldering iron, which connects to the thermocouple. At some point we're going to add maybe 20 volts to these two terminals. We're going to put 20 volts in there at some time to heat this element up. So when we're putting 20 volts in, we don't want that 20 volts to go into this operational amplifier, otherwise it's just going to fry it. This can only take a certain amount of voltage either side of the VCC and ground. It can, if we're supplying 5 volts to this op amp, we can't put any more than 5 volts, and ground is 0, we can't put any less than 0 volts in. Otherwise it'll just fry the gates and stuff that's inside the components inside the operational amplifier. So we've got to keep it below our 5 within our 0 to 5 volt range, but we're talking millivolts anyways. So the way this works is, when we're applying 20 volts here, this resistor is going to act as a load, so that we don't fry these two diodes. And what happens is, when we're at 20 volts, so we've got positive coming in on here through our load to this diode, the forward voltage, it will pass current, because the 20 volts is greater than the forward voltage of this diode, which will then go to ground. So basically, this resistor is acting as the load, so it doesn't go bang and cook the diode. But now let me get this right. But while we're below this just stops the spikes going in the opposite direction, basically. So it's this one that's the most important. But whilst we're below the forward voltage of this diode, when we're below this voltage, this can work. So when we're not so when we're not applying 20 volts to this the input, when we're not applying 20 volts to the heater element to heat it up, we can take readings of this of this line, take readings of this line to the thermocouple. What happens is, when we're not applying 20 volts, I'm just going in circles, when we're not applying 20 volts to this, we can actually then look at what voltage is coming off this thermocouple to get the temperature, because basically we've this coil, when we're not applying current, it's not doing anything, it's not heating up or anything. This coil is now acting just as a connection, as a wire to the thermocouple. So the voltage from the thermocouple can go through the coil and out of here, and it can go to our input on our op amp. But because we're in the milliamps, in the millivolts, we're below the threshold of this diode. This diode will not actually conduct any current through it. So basically it's effectively acting as a switch. So while we're reading the voltage coming into the op amp when the current to the heater is turned off, this is also turned off. But when we're applying current to the heater element, the 20 volts, this becomes turned on because it's above the threshold voltage, and this takes the load while this is on, so it doesn't fry the diode. And then but at this time we're not actually taking any readings from the thermocouple. Oh, I hope that made some sense. Anyways, back to the op amp. Yes, so we can adjust this, and we can adjust the gain that comes out of here to calibrate our signal coming out. And basically this is just acting from here to here, and this one is acting as a voltage divider to set a reference voltage on the input, and then the milliamps that we're getting out of here then sort of correlate with this voltage here and amplify it and send it out of this output. Okay, I'll pause there for a moment. Okay, so here we have the circuit, basically what I've drawn, and I have my meter on the output and ground. So we can see that the op amp is multiplying the, well, let's put my meter on the input as well. So this is my input wire. So if I just put that on there, oh, we've got a minus figure. I don't know why that is, but that's supposed to be the input from the op amp coming from this. It's probably because it's stone cold, and oh, we haven't. Yes, that's the other thing I nearly forgot about, is the cold junction voltage. The cold junction voltage needs to be taken or added to the hot the hot junction voltage or something like that. Let's just warm it up. We should get a positive. Yep, there we go. We've got a positive now. I've warmed it up. So basically we're getting less than a millivolt on the input. And on the output we've now got, well, it looks like it's multiplied it by about 150, well, a lot more. I can't remember what the number was. And what I'll do is I'll just warm it up again. So warm it up, and we can see that it's going up rather rapidly. Right, so yeah, so this is basically what Richard's already showed you. But so we've got now we've got the output on this wire, which I am now sending to this microcontroller here, and this microcontroller is wired up like we did with the 7-segment displays. So I've got the 7-segment displays wired to this microcontroller, and if I move my meter out of the way, we can see that we've got a number. Oh, right. I'll tell you what. I'm just going to pause it there because I need to get me my ceiling light on, because I'm going to turn the hang on, where's my finger? Right, yeah, pointed up. Well, the light shining on here is from an LED, which is powered by pulse width modulation, which is running at a different frequency to what our LEDs are doing, which are multiplexing. I couldn't think of the word before. We're actually multiplexing the LEDs, because only one segment is lit at one time. I don't know if well, you can obviously see it. So I'm just going to pause a moment. Right. So I've turned my small LED lights off, and now I've got my mains LEDs shining on, and you can see that we've now got a more steady display. The lighting's a bit crap because I haven't actually got the sunlight coming through the curtains either. But basically you can see there that now what we have is we have the tip with the thermocouple in, and that goes to the input of the operational amplifier. Let's try and get that a bit sort of better lighting. I don't know. I think that's the best I can get to compensate for light. So we go through the amplifier, and the output is amplified from this white wire, which we then go into our microcontroller. Our microcontroller converts that analog signal into a digital signal, and then it uses that converted analog signal to do some calculations. That now with the thermocouple there is the cold junction voltage, and then there's the actual voltage we're actually reading. It needs to do some calculations. There is a linear scale that normal K type thermocouples relate to. You know, as the temperature goes up, they give out a certain voltage, and so it uses those calculations then to display the value on the 7-segment displays. Now you can see it's pretty cool. Like I say, that the values are going to be not perfect at the moment, because for one thing we're all plugged into a perf board, you know, like a solderless breadboard, and I tell you the connections are not good on these things, and I've got no capacitors to sort of smooth out the connections on these things. And anyway, when I'm plugging capacitors in, whether they're connected or not is hit and miss. So basically it's just a guide to start with. Once they get onto the PCB, we can take some better readings and we can do some better adjustments. So all I wanted to do was show you. I'll just stick some heat onto that, onto the end of the tip again. Are we in focus on that? I don't think we are we? So let me just click on that. Is that better? Actually, that's a little bit better, that, isn't it? Right, so I'm just going to light up the rocket engine. So I've got my rocket engine going, and then I'll just warm it up. And we can see there we're now about 100 degrees, 150, 200 odd. Oh, that's my meter peeping at me. 350. Right, I'll leave it at that. I'll let it cool down again. What if my battery's low on my meter? I've had it on. Hold on. There we go. Yes. So there we can actually see the values. So this video's been really long. I think it's longer than what I expected it to be, actually. Generally down to me just waffling on, and I'm waffling now, so you know what my videos are like. So I'm going to do a part B. I'll call this part A, and I'll do a part B where I'm just going to go through the code. So you see this wire coming out of the op amp. I'm going to do a section just what happens once the analog voltage goes into the microcontroller, and it uses the analog to digital converter to convert it into value. So I'm going to do the code separate, and I'll leave it as it is at the moment. So you've got a good idea of. I thought I'd touched the bloody thing then. Yeah. So you've got a good idea of how things work. On let's bring the circuit back up. Yeah. So I'm hoping that you've got a good idea now of what's happening inside the soldering iron when it's plugged in and it's connected to the operational amplifier. And this all enforces what Richard has already said. So we've got an analog signal coming up through this feedback pin, and this goes all the way to our microcontroller up to here to pin 23, and there's also a reference voltage. Well, this is a separate thing altogether again, because a microcontroller can actually just, well, if we just look at it like an Arduino at the moment, we'll just use the internal reference and it will just give us a value. But to be more accurate, you want an accurate reference voltage, and that's what this bit here is doing. It's giving an accurate reference voltage to the microcontroller to compare this actual signal with, and then it does all its mathematics. And so what I'm going to do is, in the next part B of this video, is do the mathematics and the code to translate things into human readable values. Okay, I hope that was interesting. I'll catch you guys later.